that router in southern France. I traced it to that. It's wrongly set up, so between Sweden and northern Lebanon, no routing. And that's common. So I say perhaps every home computer in the world can reach perhaps 98% of the other home computers. We normally don't notice that because web servers are in server hosting sites, and they're normally more reachable, because if they aren't, people complain, and the people taking care of routers fix it. But so not everyone can reach each other, and sometimes it's because of badly configured routers. Sometimes it's because there is congestion, too much traffic in some area. Okay, network layout. So how should we connect these nodes? How should we organize them? Well, there are some approaches. This is the simplest of them all, a two-dimensional grid, very simple to understand. Unfortunately, it's actually pretty bad to code, because you have to take care of lots of exceptions, like if you see it's a hole in the network there was a node there and it left some minutes ago. So now we have a hole. We have to repair that hole in some way. That's lots of code and means lots of messaging between the nodes to fix that problem. So, and also it has a problem since it's two-dimensional. The distance from the nodes in the corners are very far away. So if you send a message out on the network, it will take a long time before it reaches the other corner. So that's bad. The other one, very popular, many networks use it today, is a hypercube. It's actually, well, it's a multi-dimensional grid. It's not two-dimensional, it's x-dimensional. And you connect them, well, if you don't know hypercubes, I shouldn't explain them, but it's lots of connections, but in a well-ordered manner. And it's very easy to understand once you understood it. But it has the same problem with lots of code. It's tricky to code, and it's tricky for the network to maintain the order. It means when nodes disappear, you have to fill in the holes and stuff like that. So it's lots of messaging and lots of code, but easy to understand. And it's nice, it's short distances. There's no really corners. There's no node that is very far away. So messaging is quick. And here comes my favorite, the random network. Small world networks are similar, but in random networks, you just connect to a bunch of other nodes randomly chosen from the whole network. So you just pick 5 nodes, any nodes, and connect to them. That means the network looks like a mess, of course. And understanding how to handle it is a bit tricky. Human brains don't understand these kind of things very well. We don't like chaos. Well, you do, you're a case communication club, but... but once you understood it, the code is very nice. Some of the algorithms are actually just 1 page of code, and it works. So it's very, very easy to implement once you have a good algorithm for it. But it takes a bit more to understand. And also, like the hypercubes, very short jump distances. Actually, shorter jump distances than hypercubes. So this is more efficient than hypercubes. This is not the most efficient structure, but the second most efficient structure there is, as far as we know. Small world networks have been written a lot about. The difference between a random network and a small world network is only that in small world networks, it's slightly clustered. You have some of your links are to nodes nearby in some way, geographically nearby, or your friends or something like that. But at least to make a small world network work and be a small world network, you have to have at least some random link to connect to the rest of the world. So from an algorithm point of view, when we put stuff on top of it, a random network and a small world network is more or less the same thing. Yeah, random networks, and to some extent also well-ordered grids and stuff like that, has one main problem, or, well, problem number 1 on my list, so to speak. It's net splits. That is, they tend to kind of split into islands and fall apart into many small islands. Most people are unfortunately not aware of this, so they build networks and then they fall apart, and this is weird, it falls apart. And then they plug in a bunch of servers to keep it together. Kazaa did that. When their servers go down, within some hours their network starts to split into islands, and after 1 week it's so many small islands that you can't use it anymore. But there's ways to solve this. In this case it's random networks. So the simplest way is do it the Gnutella way, the Gnutella network. They use what I would call a node address announcement. Each node now and then sends a little message that is jumping out over the network, more or less randomly, announcing, here I am, I'm this node with this IP number and you can connect to me. And it jumps, say, 10 jumps away, randomly. And that means that after some time, many of the nodes within 10 jumps from you know about you. So when they need to make new random connections, they can connect to you or someone else who have sent them an announcement. This has one big problem, that your messages just goes tops 10 jumps away. So when you choose new links, all those new links will be within the 10 jumps closest nodes. So that's some clustering. That means if you do it wrong, it splits. So a better way is to use a random walker. That is, each node has one separate connection that they use just to connect to nodes and walk around in the network. So the first 10 walks jump you do is like the address announcement is jumps 10 jumps away. But when you have jumped 10 jumps, when you go another 10 jumps, it means you will be further and further away. You won't be jumping around in your close to yourself. You will be walking far away over time. So that makes it much more random. And that means that the links between, let's say like these two islands, if some node that wants an extra link, it's a big probability that the new link will be across to some other island. And in that way make the island less of an island. I call that my island ripping effect, because it rips islands apart or really rips them together. And there is a third solution that unfortunately I don't have the time to explain, but it's similar to random walker but even more random, and that's what I call a chaos net. It's actually a network in itself, but it's more efficient and more random, more perfectly random. I like perfect randomness, it has some advantages. Yeah. Next problem is flooding. Too much work for a node. Too many trying to connect to it, or too many trying to send messages through it, and so on. Congestion, really, as we have on the internet also. And there is some solutions to that. One is to have round-based algorithms. Like in your algorithms, everything that is done, say, once a minute. So you exchange data with other nodes, say, once a minute. And you never do more than that. And that means the ones you're talking to, you don't load them more than once a minute, one message per minute. So that kind of keeps the messaging a bit more controlled if you design your algorithms so they work round-based. Another way is to use throttling. That is, if you get too many messages, you just refuse to work. You start throwing away messages and don't send them on. So if someone's sending you a message and asks you to forward it, you just refuse, because I can't do more work. So that's what I call throttling. It's primitive, but it takes care of the really bad happenings when too many nodes are sending you messages. And the third one is randomized algorithms. That is, if you use a lot of, like I say that peer-to-peer networking is chaotic. It's lots of chaos. Nodes going online and offline. They are in different parts of the world and so on. And if we can instead use more randomness, we make it even more random, then things start to smooth out. You know, if you throw a dice many times, 1,000,000 times, you get about as many ones as twos as threes. And we can apply this on peer-to-peer networking. So first make it more random, and then when it's random, it's smooth. And when it's smooth, then you can make order on top of that. Yeah, so let's look at one algorithm that runs on top of a random network or a small world network or even some other network structures. And this algorithm is actually both round-based, throttled, and randomized. So it's all three of them. And it's what I call throttled, balanced, slotted broadcasts. So actually, the title isn't complete, but it wasn't space enough. So I'll explain what it means. Let's just check my papers, because I'm starting to forget about it myself. Yeah, the basic assumption here is when you broadcast a message, it's actually not necessary that, it stands there, that the message reaches the whole network. Say there's 1 million nodes, you have something to tell the world and broadcast, you normally don't need to tell all 1 million nodes about it. It's enough that normally it's more important that the node that is listening hears enough many messages. You want to receive 10 messages a minute. You don't want 1 million messages a minute. So that's the assumption. So what we do, for instance, with the Nutella network and many other networks today, in the messages that you broadcast, you put a time to live counter. And you set it to some max number, and when it jumps across the message, each node is lowering the counter, and when it reaches 0, they don't forward it further on. That means you just reach a limited amount of nodes. That's the normal way to do it. But I find that a bit stupid. There's a better way. You can actually turn the counter around. Instead of counting down to 0, you can start at 0 and counting upwards. Not a big difference, but it makes a big difference. You see, if there is 1 million nodes, and there is only one node broadcasting, then of course you could broadcast to the whole network, no problem, because there's only one talking. But if there is lots of nodes broadcasting, like every node, then every node will get too many messages. What I do then the throttling kicks in. That is, you don't forward every message, just forward some. And you do it in a balanced manner. That is, you only forward the messages with the lowest jump counter. So that means, for instance, if too many nodes are, if say all 1 million nodes are broadcasting, and you're only allowed to forward 10 messages a minute, then each node, and you have 5 links per node, 5 incoming links. That means each node will only receive 50 messages, because the throttling prevents you from getting more. But you will get the 50 youngest messages, and that means that each node that is broadcasting will reach the 50 closest nodes. And everyone gets 50 messages, and that's usually enough in most cases. If there's only 10 nodes broadcasting in the whole network, they will reach the whole network, because everyone is accepting 10 messages a minute. So it balances. So it's just turn the time to live counter on and make around and make it a jump counter, and then it gets better. Yeah. Oh, and one more thing about slotted broadcasting is if there's different kinds of messages in the network, you should balance them individually, because if some kind of communications have lots of messages, it will drown out the other type of communication. So you should treat them separately to not drown out each other. Okay, here is a little what we can do. Everyone is thinking about file sharing and communicating, but there is other things we want to do. For instance, we want to count how many nodes are online, how many nodes are in the network. Every peer-to-peer network that I know of uses a server for that, even Nutella networks. But we can do that in a distributed manner. We don't need servers for that. There's actually 3 ways to do it. Sorry, I don't have the time to tell you how to do it. You can ask me afterwards. And it's very simple to understand how to do it. Another thing that would be nice to know is how many unique nodes per month. You know, some nodes connect an hour a month, and they get offline again. So they're a bit trickier to count, but you can count them too, without any central service whatsoever. A bit trickier, and I don't know anyone else who has solved it except for me yet. Probably some more, but no one has written a paper about it yet. There's other things. We can network averages. Every node is announcing some kind of measurement. For instance, how many files I have on my disk, the ones I'm sharing. Then you can take an average for the whole network. There's several methods to do that without a server. Another thing we can calculate is the median value. That is, how many here know what the difference between medium and median? Can you raise your hand? Okay, I think many knows. I won't go into that. It's a slight difference, but I can also do max and minimum values. Very simple. Oh, sorry. What I cannot do, and I'm a bit ashamed of it, I can't do percentile values yet. It sounds simple, but I haven't solved it, sorry. Probably to take some months studying it some other time. I can do network totals. How, for instance, number of files total in the network or number of megabytes transferred in the network the last hour or whatever you want. That we can do. And we can agree on the network time. That is, all nodes can agree on what the clock is now within some seconds or so. That time might not be the real world time, but at least they agree about it. And that can be nice when you want to do logging and stuff. So logs agree. I should mention all of these statistics, none of those